So, lost my voice a little bit after one that I guess I'm not used to talking as much as I was. So, need something clarified. Make sure you ask me. So we left off, right? We were talking about different types of variables. So I think we went through the two different types of qualitative variables. So we had ordinal and nominal. We also have quantitative variables, and those are going to be right numerical values. So a variable where when we record it for every observation, we're recording a number. So there's really just maybe two types. We'll do a little bit with both of them throughout the semester. So the first one's discrete. So discrete basically means that the recorded values you can see, there's gaps, right? So question might be like, how many siblings do you have? Well, you can tell me 0, 1, 2, 3. Right? Hopefully you don't have like 1.3 siblings. You can't have a third of a sibling lying around. So anytime for the sake of this class, when you want to think about discrete, is we're only going to see integer values as what we're recording. If you ask somebody the number of days out of the week that they do something, so here I've got how many days out of the week do you consume alcohol? Well, if you've already drank today, right, that counts as one day. So you can just drink half, right? Once you do it on that one day, you're automatically one. So there's going to be certain variables that we can only see integer values. Those will be discrete for us. Okay? So you got to do a number line, right? You can see what numbers I choose, 1, 5, but we can't see 7.34, right? We can't see anything in between if it's a discrete variable. Okay? On the flip side, we have continuous variables, which is basically that there's no gaps, right? So this would be like if I looked at somebody's height or weight, if I had a good enough measurement tool, right, I could measure this out to whatever decimal point I want, right? Here I cut them at 2 decimals and 1, but right, if I use water displacement in my knowledge of physics, I can actually get your weight out to whatever decimal I want. Not me personally, I couldn't do that, but other people can do that, right? So for the sake of this class, it doesn't matter how many decimals we see. Anytime you have a variable where you see the recorded values have decimals associated with them, think of it as continuous. Okay. So income's another one where we can see 2, we can see 5, we can see 6.3175284. Right? Any value that's continuous. So if discrete means that there's gaps, and I said already for this class, that's just going to mean anytime we have a variable that we only have integers for, that's discrete. Why could you, though, maybe purely on the definition, argue with me that salary is actually discrete? All right. Technical definition is there's gaps in between the values. Yeah.
It's not hourly, it's a daily wage. That's going to be an exact number.
Yeah, right. So if we've got like an annual wage, right? It's going to be maybe this number, right? 32 cents. What's the next value you can see? Next highest value? 54,791 and 33 cents. So technically, right, you could never see anything in between the 2 decimal points, right? You can't see 0.3256 because pennies are our lowest denomination, right? So if you really want to get technical, you could say that's discrete, but for the sake of this class, and honestly, it approximates to what a continuous variable would anyways, anytime we have any decimal points, right? So anytime you see decimal points, think continuous. Anytime we only see integer values, think discrete. Yeah.
So is that with all money or just the annual salary?
I mean, really just it depends on the variable, right? If you can measure a variable, out to, if you are doing like an hourly wage, you're probably going to be able to come up with any decimal, right? If you divide it by a certain number of hours, right, we're going to have an infinite combination of, of hours worked and salaries. And so we could see any decimal. I just kind of tried to make the point here, like, let's not get too hung up, right? Anytime we see decimals, we're just going to treat those as continuous. Any other questions on that? You good with that? So we go back to that data set I kind of showed you last class, right? Salary here, we're going to treat as continuous. I dropped the decimals out to make it look nice, but there were a bunch of decimals associated with it. So we'll go through these pretty quick because it's not going to really have that much of an influence on what we're doing. We're just kind of mentioning it and we didn't get to last class. So we've got different types of data sets we're going to look at. The first one, and probably the most common, is going to be cross-sectional. So this is just when we have a bunch of different subjects. So this could be, I've got 20 people and I'm recording their height all on the same day, right? All at the same time. Or it could be I've got 30 countries and I'm measuring their GDP in 2018. Right? So multiple subjects, recording whatever variable I'm recording at one point in time. That's going to be cross-sectional, and I'll show you some visuals here in a second. Time series is when I have one subject and I record the variable across multiple points in time. So this might be like I have one country, maybe Canada, and I record their unemployment rate over 20 years, right? Or I've got one individual and I record what their grades are every semester, something like that. Then if we throw those two together, we end up with a panel data set, right? So the panel data set, I've got multiple subjects across multiple points in time. So this would be like if I had 20 countries and I recorded their GDP in 2011, 2012, 2013, all the way to today. Right? I've got multiple subjects, multiple countries at multiple points in time, multiple years. Right? So kind of mashing those two together, time series and cross-section will give us a panel data set. And we really won't be able to do a whole lot with panel data sets in this class. Or probably kind of the next class we're taking statistics. We learn we've got some issues when we deal with panel data that we don't in the others. But like I said, for the sake of this class, I'm just going to introduce them. There are different types of data sets. So we look at cross-sectional, that's multiple subjects, so multiple countries, and I've got 3 variables which I recorded, but all in the same time period, which was 2011. Right? So that's my cross-sectional. Time series would be like if I had the US, and for what, about 10 years, I've got the unemployment rate. One subject, multiple points in time. And I have another old data set. I've got ISTEP scores for anyone who took it in 2009 through 2011 in Indiana. So I've got multiple students, right? I don't have their names, they're just identified by a number, but I've got multiple students, student 1, 2, and 3, and I've recorded their ISTEP scores in 3 different years. Multiple subjects, multiple time periods. Okay. Any questions on that? Like I said, this won't influence too much what we're doing. Just kind of trying to introduce some ideas here. So some more kind of definitional stuff to get out of the way before we jump into some stuff that's a little bit more, I think, interesting. So one thing that we're going to also have to deal with is that we have differences between population and sample data sets. Okay. Now, this will influence the way we calculate certain statistics, and once we get to those statistics, we'll talk about that. But we've got populations, which is basically every subject that if you had a population data set, it would be a data set that has every single subject in the group that you're interested in making inferences or making statements about. So if I want to say something about the average income in the US, the population data set would be every single person in the US, right, earning income. That's how it will be my population data set. Now, it's not very feasible. So more often than not, right, we try to do it with a census, but it's very expensive. That's why we only do it every 10 years. We'll talk about why maybe even the information isn't always that accurate or as useful. So usually we're just left with a sample. Right? All this a sample means is a small subset of that population. So if I'm interested in the average income in the US and I only have a sample data set, that might be I have only 1,000 different people, right? And I'm using that sample to make inferences about the population as a whole, right? Because to get population data, right? Where am I at here? It's just very, very expensive to get population data. So a lot of times we're going to resort to just using a sample. Right? So I mean, it's, we live under resource constraints, and so we make the best decisions. Often we have a sample data set of the population. It's also not practical sometimes. So the example I always give is, let's say we're concerned about obesity in the United States, right? So I go out and I'm going to get population data. I'm recording every single person's weight. I go out and I measure every single person's weight around the country. I come back, I've got this population data set. I calculate the obesity rates. Why might I be wrong? It's going to take me a really long time to record all those weights. By the time I'm done, what's probably happened to some of them? They've changed, right? So now my population data isn't even accurate, right? Because it took me so long. So sometimes it's just not feasible, but sometimes it's not practical either, right? But I can go out and collect 1,000 different weights pretty quick. Okay? So I'm not going to waste too much time on these either. I'm not going to ever ask you like definitional type questions. But we're going to start talking about some statistics, probably not as much today as we are Friday and next week. We'll call those descriptive statistics. It's just measures that we're going to calculate that tell us something about the data, right? That's really going to be the main goal of this class, is to come up with descriptive statistics and eventually move past those, but that's where we're going to start. And then I already mentioned this idea, but we're usually going to have sample data. And so whatever descriptive statistics we come up with about that sample, we're just going to make inferences about the population because we don't have the population data. It could be that our sample is skewed and it doesn't look anything like the population. So an example I would always give, like, let's say I was interested in something about Ball State students. I happen to be, I don't know, hanging around Worthen, and I start asking random people, I start to measure their height. Right? I want to know the average height of a Ball State student. Well, let's say I sample 100 people, but it just so happened that basketball practice was getting out and I didn't know. Well, now I've got this sample that's got way more, basketball players represented than the student body as a whole. And I'm going out on a limb, they tend to be a little bit taller than kind of the average student, right? So now my sample looks nothing like the population. So that can happen. And we'll address those type of issues as we start to kind of progress through this course. But that's the best we can do. Can't get population data. All we can do is use our sample to make inferences about the population. Okay. All right. So we'll start kind of actually getting into a little bit more calculations or math and thinking about how we describe data. Right? So let's say I've got this really simple data set. I drop the pluses and minuses, and only have 5 possible responses for letter grade: A, B, C, D, or F. We're living in that world, right? No incompletes, no withdrawals. We've got a nice and easy data set. So if we wanted to come up with what we call a frequency distribution, which a frequency distribution will tell me something about where the majority of responses are, right? And we'll kind of see what that relative in a second. All I'm going to do is go through every possible response I could see for the variable I'm interested in. So if I'm interested in grade, I could see A, B, C, D, or F. Right? I'm then going to count the number of students who got A's, write that down. Count the number of students who got B's, write that number down. So on and so forth. Now, with 5 responses, that's pretty easy to do by hand, right? If I was instead, I don't know, going through a used car data set and trying to record the number of specific make and models, right? I'm going to have a lot more possible responses I can see. It's going to take me a lot longer. But I'll kind of, I don't know if we'll get to there today, but Friday we'll look at Excel for sure and start to see how Excel makes this a lot easier for us to do. So this frequency distribution tells me something about where the majority of the responses are, right? Most people in this class, the most frequent grade was a B. Looks like A's and C's were fairly kind of equally as common, and then not as likely to see someone get a D or an F from this data set. All right, so very quick snapshot, and kind of get an idea of what the distribution of this data set looks like. What else did I want to say? Oh, so it is very easy, with a small data set, to count them by hand, it's very easy to do. But one file that I'll use for this course to show you different things is I have a data set that has like the names taken off of it. It has every grade that I've ever given in my stats courses. It's like over 1,000 students at this point. I don't want to count that by hand, right? So Friday, like I said, we might introduce Excel today, but we'll really get into Friday. How do I use Excel when I have a big data set of like 1,000 students? How do I get Excel to create this for me? Basically to count it up for me, so not to do it by hand. But that is the idea behind what a frequency distribution is. We can then push it a little bit further. Right? So, with the raw numbers here, it's a little bit easy to see like, oh, 3 is much higher. But let's say I've got, I don't know, 30 possible responses for a variable, right? And I've got the frequency of each possible response. It's going to be a little bit hard to kind of look through. So, okay, where's the largest value? What's the next highest value? Right? But this is an easy one. Right? So sometimes what I might want to do instead of just showing the frequency is show like what proportion of the responses were A's. So how many do I have? 4, 5, 6, 7. Let's think of a different data set. Let's say I had a data set with 10 students and 3 of them had A's. Right? And I want to turn that into a proportion. What proportion of the students would have A's there? Just 3 out of 10, so 3 over 10, 0.3. So to turn things into proportions, we are simply going to divide by the total number of observations we have. So I have 10 students, and I take the frequency of 3, divided by 10, turns it into a relative frequency, or we can think about it as a proportion, right? Proportion of students who got A's in that scenario is 0.3. So that's all our relative frequency is. You take each category's frequency, and you divide it by the total number of observations. Right? In my example, the total number of students in the data set. Okay. So what's the highest relative frequency I could ever see? It'd be a very boring data set. 1, right? If every single person in my data set got an A, right, then I have 10 out of 10 students, I'd have a relative frequency of 1. What's the lowest I could ever see? 0, right? If 0 people got A's, 0 out of 10 is 0. So I know my relative frequency should be between 0 and 1. If I ever get a relative frequency that's not, I know I made a mistake. I hit an extra button in my calculator or something, okay? So it's pretty easy to do. So we go back and think about like a baseball team's roster data. We have all these different positions, like we said. This could be a company with 9 different positions in a company. We've got a total of 25 players here. Yeah. Oh, so all we're going to do is take each category's frequency and divide it by the total number of observations. So if I have something like this, I've got all my frequencies here. To turn these into relative frequencies, all I have to do is what? Divide those by 25, total number of observations. Here, I've got 25 people on the roster at the total number. Made it easy. Sometimes you don't have that total, you have to calculate it for yourself. So I go ahead and I start dividing everything by 25, and I come up with my relative frequencies. They're all between 0 and 1. And you know, this really kind of shows me, it's kind of easy to see here with the frequency 13 is quite a bit higher, but how much higher? Well, if I'm looking here, it's about 0.52 out of the whole of 1, whereas these other positions are only like 0.08, 0.04. So it kind of makes it stand out like, yeah, this is where the bulk of the roster is in this one position. What should these relative frequencies add up to? Yeah, someone's holding their finger up. 1. Why? Well, notice I've got the same denominator, the total number of observations, and what's in my numerators? Just the frequencies. Well, if I add all the frequencies up, I should just get the total number of observations, right? Every observation is going to be recorded once, right? It's going to be, you know, if I look at a player and he's a third baseman, he gets counted once and third. So I'm counting every player once. So that if I add up all my frequencies, I'll just be adding up every single player or the total number of observations that I have in the data set to begin with. Okay? So my numerators will all add up to the total number of observations. I'm dividing by the total number of observations. Anything divided by itself is 1. Well, zoom things in front of it, but you can imagine if you add these up here, you're going to get 1. Okay? If you ever get to this point, like in the first Excel assignment or in the Connect assignment, if you have relative frequencies and they don't have to add up to 1, you know you made a mistake. Right? There's something that you accidentally hit a wrong number. Okay? Any questions on that? That's it. All right. So let's push it a little bit further. So at this point, we're looking at frequency distributions of qualitative variables, right? Positions, grade letters, those were non-numerical values. Okay? So we can go through and come up with these relative frequencies, but the way we talk, right, and the way that we usually discuss numbers, we wouldn't say, oh yeah, on this roster, a proportion of 0.52 of them are pitchers, right? We typically talk in percentages. So if I have a relative frequency, right, you kind of think about 0.52 out of the whole of 1, right? If I want to turn that into a percentage, how would I do that? Yeah, just move the decimal over 2 places, right? If I've got 0.52, kind of usually we don't like really think through what we're doing. We look at, oh, that's 52%. Right? 52% of the data is pitchers here. Well, that process you're actually doing in your head, all you're doing is taking that relative frequency and you're multiplying it by 100, right? This was just the equation for the relative frequency. To turn it into a percent frequency, you just multiply by 100. And that's typically how we talk, and that's the reason why we're going to often see this, right? We talk in percentages, we don't talk as in proportions a lot of the time. Okay? So that's nothing too crazy. So I'm going to show you something that would then, like, let's say we work through all this. I'm not going to use the iClickers until Monday. So a couple of you have let me know. I think the bookstore's out of them, and you've ordered them, and you're worried. So Monday will be kind of the first day we start using those. I'll give you a sample question today. Another thing that I wanted to mention, I forgot to mention last class. For iClicker or for class attendance, if you ever have like a university sanctioned event, that would include like you're part of a team here, or if you ever do something that's like career related. So a lot of times we'll have students, especially towards the end of the semester, have interviews, right, for internships or for jobs. And so if you ever have like something that is scheduled for an interview, come to me ahead of time, like come to me before the class, but I will excuse absences for university sanctioned events and for anything kind of related to like career building, like getting a job, so if you're interviewing or something like that, because that's the point, that's why you're here, right? So why am I going to penalize you for trying to go out and do that, right? So, but same kind of rules apply. Let me know ahead of time, and I can help you out if you let me know ahead of time. Okay? Any questions about that? So we worked through a bunch of this stuff. At this point, I would usually show you like, this is what an iClicker question would look like. I give you this data set, okay, here's all these different causes of death in the old time period, 2000 to 2007. What's the percent frequency of deaths that come from malignant neoplasms, which from my understanding is basically cancer. But how would I come up with that? Right? Yeah, everything you need here. Yeah, this one right here. Yeah, so I take that 4.4 million divided by, I was kind of nice, I gave you the total here. If I didn't give this to you, you could have come up with a total by simply adding all these up. And the reason that works is because this one's a catch-all category. It's every other cause of death. So I take that 4.4 divided by 16.6 million. Now this is where we have to do some computation in this class, but let's not get like lost in the weeds and forget what we're trying to do. We're trying to come up with the percent of deaths in this time period that came from this one category, malignant neoplasms. Well, 4.4 out of 16.6 million, I'm not amazing at doing math in my head, but I know that's around a fourth, right? 4.4 is, it's not right, little off. But I know my answer should be somewhere around 25-ish%, right? So before I even hit my calculator up, hopefully I can kind of see that just looking at those two numbers and remembering what I'm actually trying to do, what statistic I'm actually trying to come up with. So 4.4 divided by 16.6, I get what? 0.2 something. What else do I have to do? I wanted the percent frequency, multiply it by 100. All right. So if I'm looking at these responses, the only one that remotely probably makes sense is A or D. D seems too far off, but I mean, maybe 14.4 and 16.6. I rounded those pretty aggressively to get 1/4. I was thinking like 4 out of 16. So we know it's probably A or D even before we put one number in our calculator. We go ahead, whoops, and end up calculating. Sure enough, we get that 26.8%. Right? Just that 14.4 divided by 16.6 and then multiply by 100. Any questions? I know I'm not writing that down, kind of saying it in words, but if you want to, if you're taking notes or something, you could kind of write down those numbers as well. But I don't think that's too terribly tough to visualize. All right. So we want to know, how can we build these graphs? How can we take these frequency distributions and turn them into graphs? Okay. So you kind of imagine, if I go back here, let's say I want to try to give a visual representation of what the distribution of this data looks like. So what I'm going to do is think about, well, I've got the percent of deaths for every single category or every single possible response. Like this distribution came from an original data set, which was just every single death that occurred in the US and then the reason, right? And then you can kind of think about what the computer program did was go through every single death and count it if the person died from heart disease, and then added those all up, got that 5.3 million. Went through that entire data set, counted the number of deaths where the reason for death was malignant neoplasm, count those up, got that frequency, so on and so forth. So what we could do, so start plotting. I'm going to shorthand this, and I'll move out of the way in a second. I could start plotting every single cause of death here on my x-axis, right? What I then could do is just create a bar graph, right? So I look at heart disease, the percent of deaths that came from that was what, 32, about 32.16%, right? And just draw a bar up to that level. Then I'll get the next category, malignant neoplasms, 26.8, right? So not quite as high. And then I just keep doing that for every single category. Now, I already had these arranged from largest to smallest. So if I did it that way, when I graph this out and kind of see, well, the majority of deaths are coming from these two. That's what it would look like if I kind of went through the whole process. And I'll go back a couple slides in a second. What this graph really shows me, really nice and easy, is the majority of people are dying from heart disease and cancer, right? All the other causes of death are relatively small compared to those two categories. And I get a nice quick visual, right? Now this was kind of weird because we didn't break it down, right? It was our catch-all category, but even if we add up all the other causes of death, it still isn't as much as heart disease and cancer. So that's how we turn these frequency distributions into a nice visual bar graph. Right? That's the process that we're going to use. Think, so I've got, we can use a vertical. We could have done this. I always do these as vertical. I guess if you really wanted to, you could have turned it on its edge and done it horizontal with the bars going out, kind of, side to side. I don't think, just for me, I don't ever think that's as good as a visual. Kind of as we go through the semester, you'll see that anytime we think about distributions, we typically think about them on kind of this x-axis. And so just by the convention, I would probably default to a vertical bar graph anytime you're doing this. And then if we wanted to, I'm sure all you all seen these in the past, we could also turn this into a pie chart, right? So I think I've got one, right? I'm sure you've seen these in like, I don't know, 8th grade science or something, right? Where the whole pie is 100%, and then you just draw bigger pies for the categories that have a higher percent frequency, smaller kind of slices of pie for those that have smaller percent frequencies. Just another visual way of saying, or of displaying, look, I don't know what orange and blue are here. They're killing more than half of the total people. And I look up, oh, okay, and now I know maybe where to divert my resources and for funding and things like that. Any questions on these? And I'll show you, I don't think, maybe we'll get there today, but if not Friday for sure. I'll show you how we create these in Excel pretty easily, right? Like, I can't imagine getting out a protractor and trying to make sure like this pie chart's exactly right, the right ratios. We're not going to do any of that. So, I think that will be the times that we do. So, can we do this in Excel? We sure can. I'll show you how we create these frequency distributions, and then kind of moving on, how do we get relative frequencies and how do we turn those into bar charts and pie graphs. So before we jump into Excel for a little bit, I just discussed this example, and this was a qualitative variable, right? The cause of death, right? We had a word. So I was counting up the number of observations where I saw heart disease as the cause of death. What if I have quantitative data, right? So let's say I want to come up with a frequency distribution for income in the US. Seems like a very reasonable thing to want to do. Okay, so what are my possible responses? I could see $0, 1 cent, 2 cents, 3 cents, all the way up to whatever Bezos is making, right? Well, I mean, at that point, I'm just going to have little vertical bars at every single possible value. It doesn't make a whole lot of sense, right? So what we're going to do instead is something like this. How many people make between $0 and $10,000? Count them up. How many people make between $10,000 and $20,000? Count those people up, write that down. And then basically, so then basically, we're going to have the same thing that we were doing with qualitative variables, but instead of like these words on our x-axis, we're going to have 0 to 10,000. And then my next category would be 10 to 20,000, and 20 to 30, so on and so forth, right? And that way I can kind of actually get a frequency distribution where it's not just very small bars because I'm looking at every single possible response that I could see for that continuous variable. Right? Or even if it's discrete, it may sometimes make sense to throw them into these classes. It might make sense to throw them into these kind of like ranges, or we're going to end up calling bins. Okay? Now, if it's discrete, like let's say I just had a variable where it was the number of kids in the household. Well, then it's just like qualitative variables because I would count the number of households that have 0 kids, the number of households that have 1 kid, the number of households that have 2 kids, and then I would kind of graph those percent frequencies just the exact same way. So all that's really changing when we move from qualitative to quantitative variables is we're going to have different labels on the x-axis, and sometimes we're going to have to create these we're going to call bins. Right? So some of the stuff, if you are using the book to supplement this class, I think they call them classes occasionally. I'll never call them classes, other than maybe at first, just so that we kind of know that both those terms are really mean the same thing, right? So these bins are really just going to be a range of values for which, if we see the variable recorded as any value in that range, it gets counted in that category. If I see an income that's between 0 and 10,000, it gets counted in that $0 to $10,000 bin. Questions on that? So when we force, well, I should say we force, when we create these bins to come up with our frequency distribution, we're still going to create it using a bar graph, but it just has the name of histogram. It's the same thing we were doing before. It's still just a bar graph. It's just because we're displaying continuous data as represented by now instead bins, we're going to call it a histogram. Okay? So I think, I guess I'll go through these before we go into Excel today. Actually, where are we at in time? Okay, yeah. So we're coming up with these bins. So I think before, and maybe someone can already see what one of the problems is going to be. So if I counted up the number of people that made between 0 and 10,000 and 10 and 20,000, what's going to be one possible problem I could run into here? What if somebody made exactly $10,000? Well, I don't have any inequalities here, so they would get counted twice. Well, I don't want that. Right? So what I'm going to have to do is make sure that there's no overlap. Right? So I might have to do something like this for my first bin, and then for my second bin, right? I'll have the equality here, but not in the bin before, right? Because if I have it in both, I could double count an observation. Right? So I've got to be a little bit careful when I'm coming up with these bins around the kind of edges of those bins, right? I have to make sure that the equality is only on one of them. Right? If I really wanted to, I could have also done this way. Right? It doesn't matter which one I put it on, but it has to only be on one.
So would you put something like that in like the legend or something to specify?
Yeah. So that would be, these would be, I was lazy with these labels, right? This would probably actually be the labels I should be using, right? Where I'm really specific about what I'm doing. Yeah.
Why wouldn't you just make the next section starting at 11,000?
You could, right? But then what happens? What if somebody makes between 11 and 10,000?
No, I'm saying just like not doing like the greater than or less than you're saying, like 11,000 or 20,000.
Yeah, like this, right?
Yeah, probably, yeah.
Well, what's the problem? If I make between 10 and 11, I don't get counted in either one of these bins. So then you might say, what you could do is keep 10,000 here and then do 10,001. Well, actually, not even that, right? I'd have to do 10,000 and 0.01, which I can do that. It's just now I've got these labels that have a lot more stuff. So you're right. You can definitely do that. You know whatever the next value would be. It's just a little bit easier. And if you have a truly continuous variable, I can't do this because I'm using the example of income. Makes a little more sense because you know where that first value is going to be. If I had it like, let's say I was doing height and I had a really precise measurement tool, and I said like greater than, I don't know, 70 inches, right? Well, I can't do 70.01 because if I have a really good measurement, I could have just 70.0001, right? So that's why it's probably just using this convention as a little bit, it avoids running into any of those issues. But no, you're thinking about it the right way. Okay. The other problem we might run into is how many bins do I choose, right? So, or how many classes do I choose? So typically we keep this under 20. Any more than 20, we're just going to have a really, really long, bar graph or histogram. Anything less than 5, it's not going to be as interesting, right? I only got 2 or 3 categories, like let's say I use income. And I say I'm going to only do 2 bins. How many people make between 0 and $1 million, and how many people make above $1 million, right? Well, that's not a very interesting district graph, right? I mean, I can already guess that the one bar is going to be huge and the other one's going to be quite small, right? So I want to have at least enough bins to where it's an interesting display of what the distribution looks like. So there's no set rule. How long should these be? So here with income, I said, I'm going to start doing $10,000 bins. Well, I still kind of run into a problem there, right? Because if I kind of keep all the bins the same length, I have to still go all the way up to whatever Bezos is making. So I'm going like 10,000 steps all the way up to, probably, I don't know how much he's making now, close to probably a billion, I don't know. Right, so I'm just gonna have this crazy long graph. It doesn't help, I can't do that, right? So how do I come up with an optimal bin length instead of just guessing, right? Guess 10,000, okay, that's not enough. I'll guess, maybe I'll do 0 to 100,000. You can use this formula, which you take the maximum value of the data set, you subtract the minimum value, and you divide by the number of bins that you want. This is going to give you kind of what this is a good rule of how to start out, figure out what your bin length should be. If you use this bin length after you plug in those values into this formula, it'll work okay, everything will be fine. It's just that you might end up with some messy numbers. I already said that I wouldn't like to have this as my label. Well, I could end up with 38,462 and 39 cents. Well, that's not a very pretty label. It doesn't make a lot of sense as a cutoff. So usually we'll use this formula as a place to start. So maybe I use it for my income example and I come up with like 48,000. I'm like, okay, that's what the optimal bin length should be. But if I do things in 50,000s, that looks a little bit more clean, it makes a little more sense. So I'll use 50, right? It's a good place to start. It lets you know around what your bin length should be, but it's by no means the end all be all. As the examples I show you in Excel, you'll see that, yeah, we'll use this as a starting point, and then we'll kind of say, but let's choose a number that looks a little bit nicer, a little bit cleaner to display on the graph. I think I've already mentioned these. So the mutually exclusive idea, the definition of mutually exclusive is that you can't belong in both categories at the same time. So this is really talking about this equality issue that we've already brought up. They must be exhaustive. You can be a little bit careful with this, like an income example. Maybe I use something like how many people make between 0 and 100,000, 100, 200, 200, 300, and I stop once I get to 1 million. Well, there are people that make more than $1 million, and so I'm not going to be counting every possible income in my data set. And so to make these exhaustive, or to make sure that every observation is counted at least once, a lot of times what we'll do is we may do something like this, and then we get like up to a certain amount where we're like, okay, I know there's observations past this point, but there's not many of them. So I might do something like anything greater than, right? Or sorry, actually this would be any income greater than 100,000, right? And kind of create these catch-all categories at the end. That's quite often how we deal with these issues and how we make sure it's exhaustive. And then I kind of, we want to try to keep these bin lengths the same as much as we can, with the exception of these catch-all categories sometimes. All right. So I have another sample iClicker question, but I think I'll save that for when we start next class. So I'll do a little bit of Excel to end the class today, and we'll pick up with it next class. So here I've got, it should be up on Canvas. Let's double check. Oh. So if we go to our section, files, in-class data, enrollment's blank, okay? So probably at some point next week, because we'll start some stuff this week and do some more next week, we'll eventually have basically created this enrollments complete file in class, all right? So I already have it up there, so you kind of know where we're going, but I want to make sure we all can kind of replicate and create that, starting with just this enrollments blank file. So let me zoom in a little bit so that we can see things. Maybe too much. Okay. So this is an Excel workbook, right? And within it are worksheets, right? So you kind of see down here, there's tabs at the bottom. Each one has different data on it. Right? So this one's got just Indiana schools. This one has every university in the US, the state, and their total undergraduates. Right? And then I've got this sheet 3 here, which is got some data we'll talk about here in just a second. Okay? So one thing I can do is rename these sheets. So if I kind of right click down here and go to rename, I'm going to call this vaccine percent. Right? So this data has every single state, right? And I think this was like as of like last week or last 2 weeks. It has the number of new cases. And where's the, oh, here it is, the percent of their population that was vaccinated, right? It's got some other things too, like the number of new deaths from COVID, total deaths kind of from COVID, et cetera, et cetera. Okay. So the way that we'll talk about things in Excel is think of it as like a grid. Like I said, when I first started doing this, if you have any knowledge of Excel, this might be boring, but they hang in there, right? So this cell right here that has the word Alaska in it is in cell B2, right? So if I go over here, anytime that I want Excel to do something for me, whether or not that's a built-in formula that it has, or whether or not that's just simply math, I put an equal sign. Right? So let's say I wanted to divide, I don't know, 10 by 45. I basically can put that math equation in here, right? 10 divided by 45, and Excel will do that math for me. Right? So that's pretty helpful, right? Just off the bat, I don't have to do a lot of math in my head if I don't want to. I can also use those cell references. Remember I said this cell was B2. If I click on this, it'll automatically put that cell reference in here for me. So cell B2. And if I say equals B2, what that's going to do is it tells Excel, take whatever's in cell B2 and display it here. So notice this displays Alaska. Now, if I wanted to copy that word down, right? And I copy and I go down here, notice when I go to paste, there's a bunch of different options. If I just want to paste the value, right? There's this paste values option. It would just put the word Alaska in, okay? If I want to copy the formulas in the cell equals B2, go back here, I copy and I paste the formula. Well, now I've got 2000, what's going on? Well, anytime we copy and paste formulas, however far away you move this, so I went down 1, 2, 3, 4 rows and across 2 columns, it'll update that original cell reference by however many columns and rows I move. So watch, B2 actually is now D6, all right? So I can't copy like kind of formulas without them automatically updating by however many rows and columns I'm moving. Well, we can use that to our advantage sometimes. For instance, let's say I just wanted to replicate all of these names again. If I right click this and copy these cells down, notice every cell reference updates, and now I've got, you know, the correct kind of state name on that same line. If I don't want that to change, let's say I just want a row of the word Alaska, right? I'll go up to this cell reference and we'll do what we call freezing that cell reference. So if I put $signs in front of both the column and row kind of values, I guess. Now when I right click and try to drag this down to copy it, it keeps that cell reference the same, okay? So it doesn't matter how many rows or columns I move it, it keeps that cell reference the same. We'll call that freezing the cell reference using those $signs. We'll see if I can remember what the shortcut is to for a Mac. I believe it's Command T on a Mac. If you've got a laptop, it's not a Mac, it'll just be F4. Or on some laptops, there's an FN key. You'll have to hold FN, F4, and notice it puts those $signs in there for me. And it kind of moves them around. But that's a nice little shortcut. Like I said, I believe on a Mac, it's Command T, okay? Yeah, I don't use Macs, but I can remember most of the commands up to this point, but I might get them wrong on occasion. So that's just a little bit of some of the stuff we'll end up using later on. I just want to kind of show you that now. I also, before we like dive into doing these frequency distributions, we can do things like create time series graphs or, well, maybe I'll hold off on that. But I'll show you how to do a graph. So we'll skip around a little bit. We'll come back and do all this next class. So let's say I had a data set that looks something like this, right? So I've got 2 different variables, health expenditures per capita and life expectancy at birth, right? And I might want to know what's the relationship between these 2 variables. Well, I can create a scatter plot in Excel, right? That's going to look something like this. So all it does is it goes through and it takes each country and it takes the value for the X variable, the value for the Y variable, and it plots that country. Then it goes to the next country, takes that X value and Y value, and it plots them, right? So all it's going to do is plot every single observation on this XY grid, okay? Where X is what? Health expenditures per capita, and the Y-axis life expectancy at birth. Well, now we can kind of get a nice data visualization. If I was thinking about, well, what's the relationship between these two variables? Maybe there's a slight increasing line. Like if I try to draw a line of that best fit this data, maybe it's slightly going up, but it's pretty flat, right? It doesn't look, you'd expect there to be a much steeper curve for how much a country spends on its healthcare and its life expectancy, but it's not what we see. Right? So sometimes when we go in with preconceived notions, the data doesn't always play out that way. But the data is what it is, right? So how can we create one of these for ourselves? And I always find this is, we have the second lowest life expectancy of these OECD countries, but like by far and away, we spend way more on health. So it's not the strongest positive correlation here. So I thought, a relatively relevant and interesting example, and I didn't know what it was ahead of time, would be to go out, grab the percent of the population that's vaccinated and the number of new cases that we see in these states. So if I want to use these as my X and Y variables, I'm just going to select these, and I can select them with my mouse, right? But another nice shortcut is if I know I want to select both of these columns, I can hold Control Shift or Command Shift on a Mac. I'm going to hit, oh, actually, I didn't want to do that. If I just hold Shift, I can go over one column. Sorry, I don't want all the variables. So hold Shift, I can go over. Now, as I'm still holding Shift, hold Control or Command on a Mac and hit the down arrow. Oh. And it selects the entire column for me, all the way to the very last observation. So once again, the way I did that, I hold Shift, I hit the over arrow, I'm still holding Shift, I now hold Control, hit that down arrow, goes to the very last observation. This is a nice little shortcut. Here I've only got 50 some observations. This is a hell of a lot more helpful when I've got like thousands of observations, right? It goes all the way instead of me having to drag my mouse all the way down. And then I'm just going to go to Insert, right? And you'll kind of see you have these charts over here. So all I have to do is select the chart I want. I just want to put a scatter plot, right? To kind of be able to see what's the relationship between these two variables. So I hit my scatter plot option, and I can kind of see here, I've got some wild outliers here where they've got, a higher percent of their population vaccinated, but their cases are still really high. If I'm looking at a line, best fit, looks like once you get to a certain threshold, getting a larger percent of your population vaccinated doesn't really matter a whole lot. But when you're still hovering kind of around 50%, it looks like there's kind of this inverse relationship where as the higher percent of the population gets vaccinated, the number of new cases goes down. Now, like I said, we've got some extreme outliers that go against this. This is by no means the end all be all, but this is an interesting first snapshot and probably where you would start to get an idea of what's the relationship between these two variables. Right? And we'll play around with some different stuff next class. I'll show you how we could add in and figure out what these states were. We'll start to build some frequency distributions. So Friday we'll start out with and probably primarily focus on working in Excel, okay? So make sure you get those iClickers registered if you have them, get registered for Connect and do those first two Learn Smarts. Other than that, I will see you guys on Friday. Yeah, if you want to, I've had some people that give it to me in person. You can also just come up.
Stats class before.
Yeah.
How much will that factor into it? You think? I mean,
most people haven't. I would say most people haven't probably taken an actual stuff. Yeah. Like I said, I try to keep usually some computation, but I keep it as low as I can. I mean, it's a stat, right? We have to do some,
Yeah.
but no, I would say the majority of people don't have
Okay.
stats, or if they have, they've,
With that.
Yeah.
with this one.
yeah, no, I would say most people don't, so I wouldn't. I think the only requirements are certain math courses, so it's not. All right,
Yeah, good one.